All right, welcome back to Stat 2050 at the University of Wyoming. We are online, and man, are we having a great time. Okay, so first thing is first. If you were watching this after watching the ANOVA videos, I did make a mistake. Not anything involving statistics, but involving the schedule. I record these a week in advance, at least. And so I was totally spacing on when we had our exam. I told you that it was July 30th. It's not. It is August 6th. So that was my bad. That was big time my bad. So ignore everything that I said back then regarding the test. Don't ignore the other stuff. But do know that you have the test. It is now this coming Thursday. If you're watching this week 7 on Monday, it's 4 days from now. If you're watching this either sooner or later, it'll be August 6th. So anyway, okay, we got that all cleaned up, figured out. And now we've got some new stuff that we're talking about this week. And thankfully, just like last week, it's all most of the quote unquote math kind of hard work is already done for you. You just have to know where to look, what to look for, and what it means. And that's pretty much that. So before we get into it though, here's the album of the week. Keeping it quick, right? 2008 Fleet Foxes. That's the first album of Fleet Foxes. You've probably heard them before. Every single song on here is just crazy. They have a really interesting sound, and I don't know. It's just really great. It's very different, especially from all the other music that was coming out in the late 2000s. I think this is really great. So check them out. Very relaxing. I think they're super relaxing. So if you're studying, here it is, right? All right, so let's get into it. Let's get into it. So last week, what we were doing is that we were essentially finding the relationship between groups, right? Group differences, right? Essentially just doing a bunch of t-tests, right? But the sort of common denominator, the thing that we were comparing, were these different levels within a factor, right? So I think one example was like fertilizer, or like a new type of drug, or doses of drugs, like that kind of stuff, right? Where we've got some grouping variable, and then we're trying to figure out how that relates to some continuous quantitative variable, right? Okay, so what we're doing today, and then in this week, is very similar, except instead of having some group trying to figure out the relationship between some group and the outcome, we're just going to be looking at some continuous variable, some quantitative variable, and how it affects some other quantitative variable. All right? So we're going to be doing a little bit of plotting with this sort of thing over here. Doing a little bit of description of the relationship, you know. Hopefully all of this should be kind of familiar from your previous math classes. I think at least one of the math classes you had to take before taking this one probably introduced this. If it didn't, that's okay. That's okay. Well, hopefully this will be a little bit of a refresher, or at least decent background info. So let's get into it. Simple linear regression, where it's essentially what I just explained, the relationship between, in this case, just two things, two continuous variables, two quantitative variables. Okay, here's the history. Here's some really old dude over here, Francis Galton. He was pretty much the father of regression. There's sort of an anecdotal story right here. I'll let you read that. But the big sort of thing is that regression, this idea of relating one thing to another, is used now all the time. And it's also kind of intuitive too. Our brains kind of naturally think in this way. So after a little bit of practice, this stuff becomes super second nature, I think. So we got the history there. Old Frank Galton, cool dude. But what's the point? So this is I think I've now given this lecture maybe like 4 times, and nobody really gets it. But when we're doing this regression thing, we have these points. You draw a line through them. What's the point? Whatever. It's a subtle joke. So just trying to stay sane. Okay, all right. So what is the point of regression? What's the point of anything we're doing in this class? Well, ideally, we're just trying to figure out relationships between either groups and something, or groups and the relationship of the data inside the group, right? And what we're doing here is we've got two things, actually, that we can do. The first thing, the main thing, I think, is finding a relationship between two or more. We'll get to the or more later. But finding a relationship between two variables, right? Kind of the English translation of that is how our outcome changes when X changes, right? How are these two things related, right? Relation related. But then also it turns out that once we kind of figure this relationship out, we can predict some new outcome, some new Y variable with our X, right? So we would just plug in some X variable, some value that falls on the X axis, essentially, whether we have that data point or not, and we'll be able to figure out kind of a good guess as to what Y would maybe be, right? Okay, so it's all pretty interesting, I think. It's all pretty interesting. There's some rules that we do have to follow, very similar to ANOVA, that we just have to check. But this is the general idea here. All right, here we go. We are visualizing the basics here. Okay, so what this is called, over here on the right, this is called a, let me get a smaller pen here. This is called a scatter plot. And what is this? Well, hopefully this is somewhat familiar. We have our x-axis and we have our y-axis over here. And we just plot these two variables on there. So what this would look like is that we would have two columns of data, whatever. This would be our x, this is our y, right? So this would be some value. I'm just kind of making up things here, right? This should bring some things back from the deep recesses of algebra or pre-calculus or calculus or whatever. But this is the general idea, right? So we have a pair of data here that show up as a dot, right? And then this pair would be like over here or something like that, right? So each point here represents a pair of data, right? And ideally this is the same person, right? And the example that I have here, the example I have here is how age here on the x-axis, and the relationship between muscle density here on the y-axis, right? So that's all fine. That's all good. We'll talk more about the details here in a second. But we've got a little bit of sort of anatomy that we've got to go over, right? We've just talked about this one dot per predictor outcome pair, right? So this represents two things. This represents this data point and that data, right? Whatever that corresponds to. Same thing here and here. Same thing for all of the dots. That's pretty cool. Now, we also have our predictor variable. We have our predictor right here. Very cool. And then our outcome. And it's always in this order, right? So we're seeing how age affects density. Always this way, right? How does this influence this? Not the other way around, right? You can kind of do some mental gymnastics to get back to kind of vice versa, but this is the general idea. We're seeing how this one is related to this one. How, if this one changes, what happens here, right? And then that's pretty much that. And then once we plot all that data with the points, we can draw a line through it, and we won't do it. There's some really intense math that goes on behind the scenes there. But essentially what we're doing is we're just trying to minimize the distance between this line and each dot, right? So this line is the best fit line. This is the best fit. And I'll put best in quotation marks, right? Because it's only still an estimate, right? But that's the general idea. We plot all the data, and then we get the computer to draw this line through it using its fancy math, right? And this is the most optimum line, right? This is the most optimum. And then we'll just, for now, for this class, we'll ignore the confidence interval band. But that's what this little shaded area is. We're not going to worry about it. That's all fine. Okay. Very, very cool. Now, this maybe brings some PTSD back from algebra. But we've got a formula for this line. we have something for this line that is totally mathematical, that incorporates this and this, right? And it looks like y equals mx plus b. Okay, we've seen that before, right? We have seen that before, where we've got b here that represents the intercept, and then m here, this whole little thing that represents the slope, right? So m represents the slope, x is something that you would plug in, b is the intercept, right? And we'll talk more about that in a second. But in statistics, we do it just a little differently than in algebra, and it's okay. We just have to use slightly different terminology, and we can already see that down here too. So we have y equals, it's the same stuff that we saw here, except it's just flip-flopped and then it called something different, right? Where b, this b looking thing here, that's beta. Beta. Very cool, right? And it just represents the same stuff, right? So in that case, beta naught, that's the intercept. And beta 1, that's the slope. Okay, so flip-flopped, right? No big deal, and slightly different symbols. And in fact, I have that over here too. So let's kind of fill these in where we saw we've already done this. So I'll just do, this is the intercept, this is the y-intercept, right? And then beta 1 here is the slope. Well, what else do we have? What else do we have in our kind of world of regression now that we're in? Well, we have only two other variables, right? We've got y, which is our outcome, which is the thing that we care about. And then we have x, which is our predictor, or our explanatory variable. You'll see it that way too. But here's the deal, is that we're just saying, how does this one affect this one, right? And it turns out that whatever this equation is right here is the thing that tells us how these two are related. It's pretty interesting. It's pretty crazy that we can do this pretty accurately too. Okay, so let's see. We can do. Oh, we've got it here too. Look at this. Look at me. Okay, so we have our predictor, right? Our the thing that is explaining this, right? We have our outcome, the thing that we're trying to kind of figure out how it all works, right? Now, and then we've got our slope, right? So let me write beta 1, right? That's beta 1. And then our intercept over here is beta naught. Now, you're probably wondering, like, what is going on here? How come the line isn't going all the way up and actually like intersecting the y-axis? Well, in regression, we only care about what we have, right? We only care about the data that we've got. So we don't know anything about the data out this way or back out this way, okay? So sometimes the intercept does make sense. And it does make sense that it will cross over the y-axis, but sometimes it doesn't, right? But all this is telling you is that if the line were to cross over the y-axis, it would be this value, whatever it is, right? The slope is unchanging. The slope is always going to be there. It's this intersecting point that may or may not be there, kind of depending on what our data are like, right? So no big deal there. This is just saying that if the line were to cross the y-axis, that's what the value would be. Okay, useful sometimes it's not. Okay, very cool. So just like in ANOVA, where we had our residuals that we looked at, right, the sort of leftover components, well, we also get that with regression too. And let's recall that, residuals, I'm used to calling it resids. The residuals is also just another term for error, for how wrong we were, right? And it's okay to be wrong, right? Wrong, right? It's okay to be wrong. That's what statistics is all about, right? We use this sort of error to inform more of the story, believe it or not. But in this case, it's a little bit easier to see the error component in regression, okay? So we have our blue line here that represents the best fit. That's the best fit line. And then these black lines connecting each point here to the line just represents how wrong we were, right? How wrong we were, correct? Still, it doesn't really make any sense, but the way I'm saying wrong and right. But we see here that this point right here is very far away from the line, right? So what we're doing here, and I'll write out y equals, let's see, beta naught plus beta 1x 1, right? Okay, what we're doing here is that this blue line, that's what that represents. But if we were to plug in this x value, whatever it is, into this thing, it would tell me that y is this. In reality, though, we know that it's this one, right? Or at least close to it if we were to do it again, kind of situation. Well, that error component is just our residual, right? So this is going to have a really high residual. Oh, the distance away from our actual point is from this line that we just drew. But like this one right here, its distance away from the line is very small, right? So if we were to kind of trace down, if we were to plug in the x value that corresponded with this data point, we would be very, very close. The equation would tell us that our point would be right here when it's only, it's not that far away from it, right? So ideally, what's happening here is that if your residual is really high and positive, your line is going to be underestimating that point. And if your residual is low, right, and negative, then your line is going to be overestimating, right? So this is some positive residual, and this is some negative residual. Okay, resid. Okay, cool. Again, not a super big deal as far as the interpretation here goes, because again, all of the work is done for you. You just have to kind of know where to look. And we'll talk more about the residuals when we're looking at the histogram of the residuals, which is what we saw in the ANOVA world too. Okay. Blah, 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 blah. You plug in your data into R or into Excel or whatever, and you'll probably get something that looks like this. Now, this is very similar to the ANOVA world that we were working in last week, right? We just have a slightly different looking output, but it's telling us pretty much the same information. So instead of me just like pointing with this thing all over the place, let's kind of break these down piece by piece, okay? So with these residuals, we actually get a 5-number summary for the residuals. So we have our minimum residual, our 25th percentile, right? That kind of border, that kind of mark, our median, and then the 75th percentile, and then the maximum, okay? And these are not including outliers. I'm sorry, they do include outliers. They're not going to have another out here for the outliers because we don't really care all too much, or at least R doesn't care all too much to report that. So the 5-number summary here is slightly different than what we've done by hand, but telling you still the same information. Okay, now the residuals, just another term for error, how wrong we were. It just tells us exactly that. And ideally what you want is, we can kind of come down here and look, is you want a normal distribution of these things, right? Oftentimes it's easier to just plot the histogram than it is to look at the actual values here. But you would want something that has that kind of symmetric nature to it, where the median would be close to 0, centered to 0, and then these two values would be up just about the same, but one of them is going to be negative, one of them is going to be positive, and then these two values should be kind of close to the same, right? Now, as you get further away, you're going to be a little bit more inconsistent here and there, which is why the histogram is much easier to kind of read. So that's why more on this later is there. Okay. Here is the big chunk of good information, our coefficients table. Okay. Now let me write this too. Cool. Okay. So we're, again, just looking at the relationship between two things, right? And in this case, let's come back to our scatter plot. Let's go back to this one here. We're seeing how age can predict density, right? Or the relationship when age changes, how does that influence density, right? Muscle density. Okay, so that's what we've got here. Well, that relationship, we're able to plug these coefficients into this thing. okay? And that's easy enough, right? That is easy enough. In fact, it tells you everything here, which is just wonderful, I think. Okay, so we get these estimates here, and in fact, let me go ahead and cross a few things out that we don't really care about. I'll kind of dot them out like this. Don't really care too much about the t-value for this. Standard error, I'm not going to worry about that for right now either, right? So we only care about the estimate, the actual estimate for this y equals beta naught plus beta 1 x, right? These directly go into our equation for a line directly, right? So we just have to plug and chug, pretty much. Okay, so we get an estimate for the intercept, the y-intercept, and the slope coefficient. And that's all right here, okay? So if I wanted to write this out, which I think I will, yeah, I will in the next slide. But if I wanted to write this out, all I need to do is plug in 156 into beta naught, negative 1.19 over here into beta 1, and that's my regression formula. What the heck? That's so easy, right? I wish algebra was like that. So you get the estimates for the intercept and the slope. The standard error, now I've taken this from another class I taught, so there's a lot of information in here that's not super necessary, but standard error is the same as always, right? We just have a standard error for the estimate, right? So it's how far off we were from the theoretical actual value, right? Theoretical actual, right? The actual average value that the thing comes from, right? That distribution going way back into the central limit theorem. Not going to worry about it, right? It's just not necessary. But the t-value here, well, the t-value, it's the same thing as the t-stat that we calculated when we were doing t-tests, right? And all that tells you is just how far away your data are from where you expected to see it, right? And we know that the denominator in that, so t, I'll just rewrite this, t equals something minus another thing divided by the standard error, right? So just like when we're measuring miles per hour, right? That's some distance per hour. We're putting that in terms of hours, right? In units of hours. Okay, so what we're doing here, same thing with the t-stat, but we're in units of standard errors. The number of standard error, we'll say units. The coefficient estimate is away from 0, okay? Now, when we talk a little bit more about the relationship and sort of the behavior of two things, we'll remember, we'll go way back to algebra, pre-calc or whatever, that if you have a slope of 0, it's going to look like that, right? We don't want that. We don't want that, right? We want there to be some relationship between these two things, right? So that's why we're using 0 here in our t-value definition, okay? Again, no biggie at all. But what we care about, just like in the ANOVA world, where we got the difference of the two things, right? We had to do a little bit of work to get to the t-test portion, but the first thing we checked was the p-value, right? And we get that here too, okay? So the p-value is used to determine if this estimate, right? So if the intercept and the slope coefficient, can they be trusted, right? Is this close to reality, right? And the smaller this is, which in this case is super, super tiny, this actually is just like maxed out how small the value it is, how small it wants to calculate, which is great, right? So it's super far away from 0.05, okay? And then we get the significance codes. Again, symbolic, helps your eyes catch differences, whatever. Not a big deal. We'll just look at the actual values, right? Okay, very, very cool. So what in the world, what the hell do we do with this information, right? Because we're trying to figure out the relationship between two things, but I don't really know what am I getting out of this, Well, that's a great question. So let's recall that we'll go way back. Okay, so we're looking at how age affects muscle density, okay? So they got a bunch of different people and then collected their age and their muscle density. We're just trying to figure out how one influences the other, how age influences density, okay? And we're going to use this line to kind of inform our opinion of that, okay? Okay, so our outcome is always y, right? And now we've got a little bit of plugging and chugging to do, right? Okay, so what do I do first? Well, let me write out this whole thing, right? So it's y equals beta naught plus beta 1 x, okay? In this case, we're only doing 1x, so I'll just put 1. Okay, very cool. So what do I need? Well, this is the intercept, and this is the slope. Okay, well, the intercept, look at that. It's actually just spelled out for me right there. So let's plug that in. 156, we'll do a little bit of rounding magic here. Okay, 15635. Okay, and that's no big deal. Okay, and then what else? Well, what do I have left in this table? In this part, this is really only the part. This is the only part I really care about. Well, the only thing I have left is this value for age. Oops, this thing, right? Okay. Well, that's not denoting the age. That's not denoting really anything, but it is the slope of the line. What is the slope? It's beta 1. We put that right there. Okay, cool. Now, one thing that you're probably already noticing is that, okay, is it always plus beta 1 x1, or can it be minus as well? Because we have a minus sign right here. We have a negative sign. Well, it can be either, right? You can write it in two ways. We can write it like this, where we have plus and then negative 1.19. Okay, but then the interpretation of this thing, which we'll get to in a second, gets a little bit kind of clunky, right? So what we're gonna do is we're just gonna put minus 1.19, okay? And maybe instead of x, maybe let's plug in age for it, okay? So we got that. Look at that. That is our regression formula. Now, you're probably wondering again, like, well, what do I do with these values? What do they really tell me? Okay? Well, here's what it tells you. Ouch. Good Lord, I just like smashed my toe on my table. I'm like, whatever. Okay. So what do I do? Okay. So we have our slope here. What do we do with that? Well, for every 1 unit increase, if we were to plug in 1 here, and then work this math out, right? So 156.35 minus 1.19, right? Because 1 times 1.19 is just this, okay? Then our density is going to be whatever it is, right? And then if we plug in 2 here, right? So somebody who's 2 years old, I'm breaking some rules here, but somebody who's 2 years old, okay, well then this whole thing, this doesn't change at all, right? We're not plugging anything into this part of the equation. We're only plugging something into this side of the equation. So it's this whole thing, right? So if we have 2, if we're multiplying this by 2, right? Okay, then that's just 2 of these. If we're doing this by, I don't know, if you have a 50-year-old, right? We can do that. Well, that's just 50 of these, right? So as we increase this value, as we increase the age by 1 unit, right? For every 1 unit increase in x, for every time age goes up by 1 year, y changes by this value, 1.19. And then I think it's what is it? Milligrams per kilogram? I think that's what it is. The units don't really matter, but that's what's happening here, right? So the intercept is staying the same always. It is always, we're not plugging anything into this to change it, but we are plugging it into this side of the equation, right? So 51, somebody who's 51 trying to figure out what their muscle density would be, right? It's going to decrease. It's going to decrease by 1.19. We'll actually even write that. Negative 1.19. Okay. Got change, but you can get directional with it. Okay. So for every 1 unit increase in age, density changes by 1.19 milligrams per kilogram. And if we're being very technical, on average is what we're saying. On average, right? Okay, so for every 1 unit increase in this, every 1 unit increase in age, as age increases by 1 year, density will decrease by 1.19 milligrams per kilogram. And that's what's happening, right? All that information is given to you. But just like with ANOVA, can we trust this, right? Can we trust this? Let's see. Do we even really need to go over this? You know what? Here's what I'm going to do. I'm going to pause the video, and then we're going to get right back into it, starting on this slide, and then we'll get into it. Okay, very cool.